Thank Right, screen share again. All right. All right, so I want to review. We're in the process of analyzing Lorentz transformations with the ultimate goal of applying what we learn to the transformations of the Dirac equation. The notation here is that the x mu is the four-dimensional space-time coordinate vector. The time component is ct. Spatial component is x, y, and z. Metric tensor is given here with -1s on the spatial parts and +1 on the time part. We define a Lorentz transformation as a mapping that takes space-time into itself. That's to say, it maps one event into another event. Space-time is the space of events. It's an event space. So that's what this means. And we're going to assume it's a linear transformation specified by a matrix lambda connecting the old event with coordinates x nu to the new event with coordinates x prime mu. And we require that the Minkowski scalar product is invariant under the transformation. That's what this equation means. It's it involves the invariant interval d tau squared, which is the square of the proper time connecting to nearby intervals here. All right. This leads to a condition on the matrix lambda. In order that it be a Lorentz transformation, we write it in matrix form by, sorry, the mess here. We write the matrix lambda as a matrix with components lambda, as you see, mu nu, where mu is a upper or contravariant index and nu is a lower or covariant index. We move it over a little bit so it can be seen a little better. These correspond respectively to the row and the column of the matrix. The little dot is a placeholder, and it just means that the mu has been raised from its lower position, and the first index is the mu and the second index is the nu. Likewise, we let G be the matrix with components G mu nu, and G inverse be the matrix of the components G upper mu nu, which is defined as the inverse of the matrix with lower components. Then lambda is a Lorentz transformation if it satisfies this equation. This actually follows directly from the invariance of the Minkowski metric. Lambda transpose G lambda is equal to G. If you want to write it up purely in terms of indices, here it is. I think you can see this is somewhat messier than the matrix equation, so we'll work with that. All right, so that's a little bit of a review of what we did with Lorentz transformations. Now, the first order of business tonight is to mention the fact that Lorentz transformations so defined include both parity and time reversal. By parity, I'm referred to the matrix that looks like this. It's got a +1 in the time components and -1 in the spatial components like this, zeros in the off diagonal. This is an example of a Lorentz transformation. You can easily check that this satisfies the condition given in the last page I wrote of a Lorentz transformation. And you can see what it does is it says that t prime is equal to t, but x prime is equal to -x. So it is the spatial inversion or the classical version of what we call the parity transformation in quantum mechanics. Likewise, there's a time reversal operation, which by our definition is also a Lorentz transformation. It has a -1 in the time slot and +1s on the spatial parts. It causes t prime to equal to -t, but doesn't do anything to the spatial coordinates x prime is equal to x. And again, one can easily show that both of these are Lorentz transformations. So part of the moral here is that Lorentz transformations defined in the manner in which I've done so include the discrete parities, the discrete symmetries of parity and time reversal. Now, in general, to get a Lorentz transformation, we end up with some full 4x4 dimensional matrix. And it's a fact that this matrix may or may not contain either a parity and or a time reversal operation. So now what I'll do is to tell you how you can tell whether it does. So let's just start with the time reversal. So let's say, we'll put it this way, we'll say lambda contains a time reversal operation. The condition is this: if the 0, 0 component, lambda 0, 0, is negative. And let me explain why that condition is true. It's because if I write out the equation explicitly connecting the old and new space-time coordinates, which in general is this, if I take the mu equals 0 component of this, what I get is CT prime is equal to lambda 0, 0 times CT, that's for the time component here, nu equals 0, plus lambda 0 I times xi, that's this term with nu equals to the spatial part, I like that. So this connects the new time under the Lorentz transformation with the old space-time coordinates. Now from this equation, you can see that partial of t prime with respect to t is equal to lambda 0, 0. And this is taken at fixed x like this. So this is the rate of change of the new time with respect to the old time at fixed old spatial location. And it's otherwise just the 0, 0 component. By the way, in these two matrices here, here's the 0, 0 component. You see, it's in the upper left-hand corner of these two particular operations. Now, the ratio of the time between the old time and the new time is otherwise what you call the factor of time dilation in special relativity. That's just what it is. It's a quantity that Jackson calls gamma, except for the fact that this lambda 0, 0 could either be positive or negative. So this in fact is equal to plus or minus gamma, where gamma is equal to 1 over the square root of 1 minus v squared over c squared, and where the v is the velocity, which is inherent in the original Lorentz transformation. If it contains a boost, it's got a velocity. All right, so that's the meaning of this. One can show that lambda 0, 0 from the definition of a Lorentz transformation is that its absolute value is greater than or equal to 1. And that means there's two cases. Either lambda 0, 0 itself is greater than or equal to 1, or else lambda 0, 0 is less than or equal to minus 1. If the lambda 0, 0 is positive, what it means is that as the old time increases, the new time increases also. If the lambda 0, 0 is negative, it means as the old time increases, the new time decreases. That means that the operation contained a time reversal. You see, it's something that reverse the direction of time. And so that's where this rule came from, that lambda contains t if lambda 0, 0 is negative. Actually, not just negative, it's less than or equal to minus 1 is the condition. All right, so that's where it came from. So it makes it easy to see if you were to look at the matrix to see whether it contains time reversal. So let's suppose we have a Lorentz transformation that does not contain time reversal, so that lambda 0, 0 is greater than or equal to plus 1. Then what we can say is that lambda contains parity, a spatial inversion, that is to say, contains parity if the determinant of lambda is equal to minus 1. As for example, if you look at the spatial inversion operation up here, you can see lambda 0, 0 is plus 1, so it does not contain time reversal, but you can see the determinant is minus 1 because it's got these 3 minus 1s here, multiplied together to give minus 1. And so this, I'll remind you, is actually rather similar to what we had in the case of purely spatial rotations. We had a improper rotation, one that contained a spatial inversion, could be recognized by the fact that the determinant of the rotation matrix, the orthogonal matrix, was minus 1, so that it belonged to the group O3, but not the group SO3. There's something similar here. If determinant lambda is minus 1 and it doesn't contain a time reversal, then it means it does contain parity. So this leads to another conclusion here is that if lambda 0, 0 is greater than or equal to 1 and determinant of lambda is equal to plus 1, then lambda contains neither parity nor time reversal, neither spatial inversion nor time reversal. And if this is the case, we will say that lambda is proper. It's a proper Lorentz transformation. This is a definition of a proper Lorentz transformation. It contains neither parity nor time reversal. Now, my reason for going through this is to, first of all, to explain to you that this generalized definition of preservation of the Minkowski scalar product includes the discrete symmetries of parity and time reversal. And then the second thing that I wanted to do was to eliminate them, because actually tonight I don't really want to talk about the discrete parities, discrete symmetries. We'll come back to, at least parity, we'll come back to later on if we have enough time in the course. We're running out. But tonight I want to talk about only the proper Lorentz transformations, which is what is left after you get rid of parity and time reversal of the discrete symmetries. So the proper Lorentz transformations, as it turns out, are made up out of rotations and or boosts, and that's all they are. It also turns out that the space of proper rotations, if I draw it as a blob here, it contains the identity. It's easy enough to see that the identity is proper. It contains the identity, but it's also a connected set, so that if you have any other proper Lorentz transformation, it can be connected by a continuous curve coming from the identity. Or to say it another way, you can build up any proper Lorentz transformation by applying infinitesimal rotations and boosts that move you along a curve and bring you out to the final Lorentz transformation. So this is a fact that we'll need to keep in mind in talking about proper Lorentz transformations. So most of what I want to do tonight, in fact, everything after this point, has to do only with proper Lorentz transformations. Now then, proper Lorentz transformations, as I mentioned, can include both rotations and boosts. And as far as rotations are concerned, we studied them last semester, so we know a lot about them. So let me just kind of review for you what we did with rotations. I've given here the 4x4 matrices, which actually are Lorentz transformations, but they're also, as a special case, they're rotations. These are rotations about the x, y, and z axes by an angle theta, as you can see. And you can see that these 4x4 matrices contain ones and zeros in the time component. By the way, in case it's not obvious, we're labeling our coordinates 0, 1, 2, 3, like that, and the time component comes first, and then the x, y, and z. That's how these matrices are organized. So the time row and the time column contain 1 and 0. Basically, the 1 here means the rotation doesn't do anything to time. And as far as the spatial part of it, what we get is a 3x3 rotation matrix, which is the same one we had last semester, with no change whatsoever. And that's just what these are. These are now the three about the three coordinate axes. So that's a little bit of a review of what we did last semester, as well as showing how this is now being written in 4x4 form instead of in the earlier 3x3 form. Now, as long as I'm talking about rotations, let me mention a few more things that we learned last semester. Oops, sorry, wrong page. Let's see, where is it? It's here. Let's mention something else we learned last semester about rotations, is that they can be written in exponential form. In axis, in hat is the axis, theta is the angle. They can be written as e to the theta times in hat dot j, where j is a quote unquote vector of matrices. You can also write this as theta vector dotted into j, where we define theta vector to be the magnitude of theta times the axis in hat of the rotation. I hope you remember this stuff well enough, because we've done this a number of times in the past. In any case, the three J matrices are listed here, 1, 2, and 3. I'm putting parenthesized subscripts here on the J matrices to indicate that what the parentheses here mean is that the numbers in there are not the components of the J matrix, but rather labels of them. There's three of them, 1, 2, and 3, and this is J1, J2, and J3. The components are given explicitly by the matrix that's written out here. Now, these J matrices have zeros in the time row and the time column. And in the spatial part of it, they're the same J matrices we used last semester with no change. And so, except for adding a trivial row and column to take care of the time coordinate, this is just what we did last semester. And these then are the generators of rotations now regarded as a subset of Lorentz transformations. And if you want algebraic formulas for the components of the J matrix, they're given here. This is just saying that the components in which a row or a column is a time is equal to 0, and the spatial parts are the same ones we had last semester. So that's a little bit of review of rotations. All right. Now, proper Lorentz transformations, however, also include boosts.
Professor?
Yes.
Shouldn't the rotations have... Oh, sorry. No, nothing.
Is it okay?
All
right. Now, so that's review. Now, the proper proper Lorentz transformations also include boosts, and we haven't talked about them before. So let me say some things about boosts. I'm assuming, by the way, that you've been through a course in relativity, so you know about boosts already. One of the things you probably know is that a boost is specified by a velocity. And a velocity, we can break it up into its magnitude times its direction. I'll call the direction b hat, which I'll call the axis of the boost. It's really just the direction of the velocity, but it's like the vector n hat in the case of rotations. And so I'll call it, use the same name for it. I'll call it the axis of the boost. It's really just the direction of the boost. Well, not quite. I'm going to allow this quantity v here to be negative. So v ranges from minus c up to plus c, up to plus c, like so. So that by making v negative, we have a velocity that's in the opposite direction of the axis. Will allow that to take place, but the velocity has to lie between plus and minus c. Now, if you study Jackson's book, which maybe you didn't, because I don't know if they don't use it anymore, but Jackson has a commonly used set of parameters for describing relativistic phenomena. One is he calls beta, which is just a dimensionless velocity. It's v over c. This ranges between -1 and +1, where -1 and +1 are basically at the speed of light, you see, measured in terms of beta. And then you have the quantity gamma, which is the factor of time dilation. It's 1 over the square root of 1 minus beta squared. And this has the range that 1 is less than or equal to gamma is less than infinity. Gamma goes from minimum of 1, maximum out to infinity. This, again, as I say, is a factor of time dilation. So this is fairly standard notation in books on special relativity. Then you may remember that you get little 2x2 matrices for carrying out boosts, and they have these components: gamma, gamma beta in the first row, gamma beta in the second row, and gamma in the next row. Let me just call this matrix M here, like this. Just M just stands for matrix, but it's a 2x2 matrix. Now let me show you how this matrix is used for carrying out a boost. Let me remind you that the form momentum of a particle is given by E over c in the time component and the usual 3 momentum in the spatial component. So if I have a particle at rest, I'll use the 0 here to mean at rest. So its form momentum p mu 0 is the energy divided by c, but at rest the energy is mc squared, so you just get an mc in the time component, and then the 3 spatial components are 0 because it's at rest. So that's the mc. Now then, what I'd like to do is take this particle at rest and I'd like to boost it down the x-axis with a velocity v, which is given by this beta here, which is v over c. And the way to do that is just take this 2x2 matrix and just multiply it under the first 2 components of this 4 vector here. That's the one that involves the time component and the x component. We do that if we want to boost down the x-axis. So you can see that if I multiply the matrix here, I can just write it out. You'll see what you get. Multiply the matrix gamma gamma beta times that column, you're going to get a gamma mc in the time component. And then what you're going to get is, and then for the second one, you're going to get a gamma beta mc in the x component, and the y and the z components don't change. Well, this can also be written as gamma mc squared divided by c for the time component. And since beta is v over c, this turns into gamma mv for the spatial, for the x direction, and otherwise you have zeros here. And you can recognize this as an E over c for an energy of a particle that has energy gamma mc squared and has a momentum p sub x is equal to gamma mv. These are the usual expressions for the energy and momentum of a particle moving down the x-axis with velocity v. So what this shows is that this little matrix here carried out the Lorentz transformation, mixing up the time and the x components and producing a particle that's moving down the x-axis with a velocity corresponding to the beta here. One thing I want to point out about this is that, so this is how you do Lorentz transformations, in this case moving down the x-axis. One thing to point out is that I'm using an active point of view here. That is to say, we had a particle at rest and we changed its state of motion by applying a boost, and it therefore transformed it into a particle that's moving down the x-axis with some non-zero momentum. And the reason I'm using an active point of view is because we now have to talk about rotations and boosts in the same breath. Last semester, when we did rotations, we took the active point of view for good reasons. It's better than the passive one. And so now we have to use the active point of view also for Lorentz transformations, and that's what I've just done here. This may confuse you some because introductory courses on special relativity almost always use the passive point of view, where you're changing from one frame to another. And I'll try to say some things moving down the line to help you not be confused about that. But I think this is pretty clear what we just did here. All right. Now, this is this little matrix M that appears here. Now I want to tell you about rapidity, because rapidity is a more convenient parameter for our purposes for describing a boost than are the Jackson's gamma and beta parameters. The relation is the following, is that the gamma, the rapidity I'll call lambda, it's a new parameter. The Jackson's gamma is given by the cosh of the rapidity lambda. Gamma times beta is the sinh of lambda. And if you divide the two, what you get is beta is the tan h of lambda, hyperbolic tangent. These are hyperbolic. So the parameters here are hyperbolic trigonometric functions of the rapidity. And that means that this matrix M, which I'll now call M of lambda because it depends on lambda, can be written this way as cosh lambda, sinh lambda times cosh lambda. In cosh lambda, you can see that it's a kind of a hyperbolic version of a rotation matrix, which is indeed exactly what it is. And it has certain properties that I want to point out. One of them is if you take the determinant of M of lambda, you get 1, because it's cosh squared minus sinh squared. Another property is this one. If you take M of lambda 1 and multiply it times M of lambda 2, you get M of lambda 1 plus lambda 2. In other words, the rapidities add when you compose the Lorentz transformations. And this is, of course, analogous to what happens when you rotate about a given axis. If you compose them, then the angles just add. This rapidity lambda is like a hyperbolic angle, and it adds in the same way that ordinary trigonometric angles add under ordinary spatial rotations. This is the advantage of working with rapidities. It has a simple addition law when you compose Lorentz transformations. All right, so this is the M of lambda. Now, based on what I've said, it makes it pretty easy to write down the 4x4 boost matrix for boosting down the x-axis. And it's going to look like this. Let me call it B stands for boost, just like R stands for rotation. Let's make B stand for boost. And let's do it this way. B stands for boost. We're going to make it going down the x-axis like this with a rapidity lambda. And what is the matrix? Well, it's cosh lambda here, sinh lambda there, sinh lambda here, cosh lambda there. And then the rest of it, nothing happened to the y and the z coordinates. So these have to be zeros here and then a little 2x2 identity down in that block. And this is really just extending to the y and z coordinates what I did earlier and multiplying by that 2x2 matrix. But it now gives us an example of a boost as a Lorentz transformation, a full matrix, now with the active interpretation written in terms of the rapidity of the transformation. Well, this is easy to generalize to boost on the y and the z axes, and so I've summarized that for you here. Let me pull up the summary. Oops, wrong one. Let's pull up the summary here. Is that this page? Let me bring it all up the full page here. Is this getting a little dark? Let me see if I can lighten it up a little bit. Yeah, lighten up a little bit. Let me try to refocus it too. All right, good. Yeah, that's good. All right. So this is a summary of boost on the 3 coordinate axes. Here's the x one that I just pointed out, that I just wrote down a moment ago, separating off the time row and the column from the 3 spatial ones, as you see here. Here's down the y-axis, and then here's down the z-axis. You can see the little 2x2 M matrix is appearing, here in this thing here about the x and the time, and here it's the y and the time, and here it's the z and the time. And otherwise, it's the same matrix, and everywhere else you just get zeros and ones. So this is pretty straightforward and pretty easy. Here again are the definitions of the rapidity in terms of the gamma and beta parameters. And and the definitions of the gamma and beta parameters as in Jackson's book. All right. So that's a summary of boosts. So now these are boosts that are taken down the 3 coordinate axes here. All right. Now what I'd like to do is to tell you how we can get a boost in an arbitrary direction. It's possible to work out a general formula for a boost in a direction, any direction b hat with rapidity lambda. And in order to do this, we use the fact that when you carry out a boost, the time component and the component which is along the direction of the boost, so as I say, the long direction b hat, transformed by that little 2 by 2 M matrix that I just been telling you about, as you see up here in this example. Whereas the other 2 coordinates that are orthogonal to that are not affected, as you see here in the y and the z. So let's introduce a 4 vector. Let's call it a mu. A is just any 4 vector here. A just means any. It's got a time component a0 and a spatial vector like this. And let's define a modified or transform 4 vector a prime mu, which is equal to a prime 0 and a prime vector. And this is equal to our boost along the direction b hat, or with axis b hat and rapidity lambda. And I'll put mu nu indices on that, multiplying onto a nu. In other words, it's just equal to this boost matrix multiplying onto the 4 vector you see directly above. So we can work out what this boost matrix is in the general case in which b hat is pointing in any direction. So we do this by first of all, let's note the time component of a is the a0, and then the component which is parallel to the direction of motion. Let me write it as a parallel. That's the same thing as b hat dotted into a. And so the transformation law is this: is that first of all we have a little 2 by 2 matrix. We have a prime 0, and then a parallel prime is equal to that same M of lambda matrix, multiplying onto a0, and then a parallel without the primes. And as far as the perpendicular parts go, we have a vector perpendicular prime is equal to a vector perpendicular without the prime. That part is invariant. Or if we write this out more explicitly, it's a prime vector minus b hat times a prime parallel is equal to a vector minus b hat times a parallel. All right. So let's write some of this out more explicitly. Let me multiply this matrix out. We first of all get a prime 0 is equal to cosh lambda times a0 plus sinh lambda times a parallel. We also get a prime parallel is equal to sinh lambda times a0 plus cosh lambda times a parallel. All right, that's just multiplying out the matrix. Now then, for the vectorial part of it, for the a vector here, let's look at that. Let me solve for this a prime vector. A prime vector, the full thing, not the perpendicular part, is equal to the right hand side, and I'll bring this second term over. So copy the right hand side. That's a vector minus b hat times a parallel. And then bringing this term over the other side, I get then a plus b hat multiplying times a prime parallel, but I can copy that from this equation here. So it's sine h lambda a0 plus cosh lambda a parallel, like so. All right. And let me pull that together into a little neater form that we can use. I have room to do it here. So it's going to look like this. A prime 0 is equal to cosh lambda a0 plus sinh lambda a parallel. That's the first one here. And then the second equation is a prime is equal to a vector prime is equal to, let me collect this up a little bit. It's given by a vector here, the first term. Then b hat times a parallel appears both here and there. So I get plus b hat times a parallel multiplying cosh lambda minus 1. And then finally there's the b hat times sinh factor, b hat sinh lambda times a0. And so this is the this is the transformation of our arbitrary 4 vector A under an arbitrary boost, which is in any direction B hat with rapidity lambda. Okay. There's a similar formula for this for a rotation taken about any axis with any angle, and it's repeated in, I think, notes number 11 from last semester. You can look it up and see. It's a very similar very similar looking formula, except you have ordinary trig functions instead of these hyperbolic ones. All right, but in any case, we now have then one can read off from this the components of the matrix B, boost matrix of B hat comma lambda. One can read that off from these coefficients. That's easy enough to do. All right. That's then the creation of the 4x4 matrices that we need in order to carry out boosts about an arbitrary direction. Now then, the next task that I want to address is to specialize to the case of infinitesimal boosts. I won't bother with rotations because we've done that already a number of times, but let's work on infinitesimal boosts. Infinitesimal operations, as you know, are very important in the theory of symmetries, and so we'll be paying a fair amount of attention to them. To get the case of an infinitesimal boost, all I need to do is to take the lambda parameter in this general formula and make it small. Let's just take lambda to a small number. If lambda is much less than 1, since beta is equal to the hyperbolic tangent of lambda, this implies that beta is also much less than 1, and that means that v over c is much less than 1. So we have velocities that are low compared to the speed of light. We're talking about low velocity boost, basically, when lambda gets to be small. Anyway, if we do, let's write out the equations here. So we get a prime 0 then is equal to, now cosh lambda is nearly equal to 1 when lambda is small. So it's like the cosine, same property that. So I'll just drop the cosh and replace it by 1. Since lambda, on the other hand, is approximately equal to lambda, so I get plus lambda times a parallel. As far as a vector prime is concerned, the cosh lambda minus 1 goes to 0. So I have the first vector, which is just a vector. The next term is 0. And then I get plus lambda times, replacing sinh by lambda just by lambda, I get b hat lambda times b hat times a 0, like so. Now we can organize this in a matrix form. It looks like this. I have a prime 0. So this is the case when lambda is much less than 1. This is an infinitesimal boost. So a prime 0 and a prime vector then is equal to, as you can see, the first column is the unmodified vector. And then we're going to get the small correction, which is due to the lambda stuff. This can be written in the following way. Lambda times a matrix here, and I'll partition it like this, multiplying onto a0 and a vector, like so. And this matrix contains 0 here, and b hat there, and b hat there, and 0 here, like so. And if you want to check this to see that this is right, just look at the first row of this. A prime 0 equals a0. That's what we have here. And then here the lambda times b hat. This is a b hat a row vector. That's going to get multiplied times this column vector there. That gives you the dot product, which gives you a parallel, which is the same thing as b hat dotted into a. That's what a parallel is. So that takes care of the first equation. As far as the second equation is concerned, you've got the a prime is equal to the a. That's the first part here. And then multiplying this second row, which is actually a 3x4 matrix times that vector, you get a b hat times a naught, a0, and the 0 block here doesn't give anything. So that gives you that correction term, lambda b hat a0. So it gives you this equation as well. So written out explicitly in matrix form then, this is what an infinitesimal boost looks like. Now, you may recall that when we had rotations, we had two different notations. One was to have theta and n hat, and we also defined that to be theta vector. As a vector of angles, it's equivalent to specifying both the magnitude of the angle and the axis. Likewise, what I want to do is to take the rapidity lambda and the axis b hat of a boost and just define this to be lambda vector. It's a like a collection of 3 rapidities. If I do this as lambda times the b hat here, it makes this matrix look like this. It becomes 0 with lambda vector there and lambda vector here, and a 0 there like that. And then this in turn can be written as lambda dotted into a quote unquote vector of 4x4 matrices that I'll call K. And what the K has got zeros in place. You see zeros here and ones along these where you see these 2 lambdas here. Let me show you what the K's are, and then you'll understand how this works. Here's the 3 K matrices looking like that. So if I have lambda 1 K1, lambda 2 K2, lambda 3 K3, it's going to give me the lambda across there and the lambda down there, and that's just what we've got for this correction term. And so what that means is that the infinitesimal boost looks like this, is that b of b hat comma lambda is equal to the identity plus lambda vector dotted into K vector like that when lambda is much less than 1. And this can also be written as lambda plus lambda scalar times b hat dotted into K. It means the same thing. These are 2 different versions of infinitesimal boosts. But in using this notation, you must remember that K is well, the lambda here is a vector of numbers, but K here is a quote unquote 3 vector of 4x4 matrices. This is just like what we did with infinitesimal rotations. R of n hat comma theta is identity plus theta times n hat dotted into J, but this is also the same thing as identity plus theta vector dotted into J vector, like so. They mean the same thing, and this is only true when theta is small as well. So these are the 2 expressions then for infinitesimal rotations and infinitesimal boosts, and you see that they're quite similar to one another. All right, now let me see if I can brighten this up a little bit. It seems to always be going dark. Maybe I'll try to focus it again. All right, good. All right, so to summarize, what we've done for boosts is we've kind of filled in all the details we already had for rotations. We worked out the meaning of boost as an active transformation. We saw the matrices for boosts along the x, y, and z coordinate axes. We generalized that to a boost in any direction. We then made the rapidity small so that we got an infinitesimal boost, and that's what we have that's being displayed here. This led us to introduce this quote unquote 3 vector of 4x4 matrices we call K, which are the our linear combinations of them specify the correction term needed to get an infinitesimal boost. Same kind of analogous statement could be made about the J matrices in the case of rotations. All right. Now then, this then leads us to a general expression for an infinitesimal proper Lorentz transformation. There's a nice theorem which I won't prove. The proof is actually would take us rather much on a tangent to go into it, but it's easy to understand the proof. The proof says that an arbitrary proper Lorentz transformation has to be proper. It can be written uniquely as lambda is equal to r times b, where r is a pure rotation and b is a boost. It's possible to take any proper Lorentz transformation and uniquely factor it into a pure rotation and a pure boost. So I won't prove this theorem, but if we apply it to the infinitesimal case, then an arbitrary infinitesimal lambda looks like this. For the rotation, I get identity plus theta dotted into J. And for the boost, I get identity plus lambda vector dotted into K vector here like this. And if you expand this out to first order, you get identity plus theta dotted into J plus lambda vector dotted into K. And this is when lambda and theta are small. So this is a general form of an infinitesimal Lorentz transformation. And these matrices that appear here, there are now 6 of them. There's 3 J's. and there's 3 Ks, they constitute what you call the Lie algebra of the Lorentz group. And the elements of the Lie algebra of the Lorentz group satisfy commutation relations, which I'll mention. If I take the commutator of 2 J matrices, this we actually talked about last semester. This is epsilon I J K J K. This is the same commutation relation as we had last semester, no change. However, you may recall that when we went to rotation operators in quantum mechanics, we ended up with a quantized version of this, which was the commutation relations of angular momenta. Now dealing with Lorentz transformations, something similar is going to happen with the K, as you'll see coming up in a little while. If I compute the commutator of the J with a K, Ji with Kj, this turns into epsilon I Jk times Kk, like this. I should really be putting parentheses around these subscripts here to indicate that they are labels of the matrices and not components. And then finally, if I take a commutator of 2 K matrices, Ki with Kj, it comes in with a minus sign, epsilon I Jk, times J sub K, gives you a J matrix like that. These commutators it's straightforward, but of course somewhat tedious. You have to multiply a lot of 4x4 matrices to do it, but it's straightforward to check these commutators. The fact that the commutator of 2 Ks gives you a J means that if you apply a sequence of boosts, pure boosts, in general, what you get is a rotation coming out. You can imagine, let's say, taking a particle at rest and applying some boost to it to accelerate it, and then you keep on applying infinitesimal boosts, like maybe it's on an accelerated orbit or something, but after a while the particle comes back to rest again. Suppose that happens. So you have a whole sequence of pure boosts, one after another, that first accelerate the particle and then bring it back to where it started from, with zero velocity, and when all is said and done. Well, when the velocity returns to zero, does that mean the Lorentz transformation returned to the identity? No. The product of all those boosts ends up being a rotation. There's a rotation in the frame of the particle. The particle had spin, you'd see it in a rotation of the spin of the particle on carrying it around this orbit. So this is the fact that compositions of boosts give rise to rotations. And this is the basic idea that it's at the heart of what's called Thomas precession, and it's important for dealing with the precession of spins, such as electron spins in atoms, when they are accelerated. This is an important issue in the spin-orbit interaction, which is one of the fine structure terms. All right. Anyway, this commutator is the beginning of the story of Thomas precession. All right. All right, so that's the story, or that's one story anyway, of infinitesimal Lorentz transformations. Now, this, however, is not a covariant description of infinitesimal Lorentz transformations, or of Lorentz transformations in general. The reason being that the decomposition of Lorentz transformation, I'm speaking not just purely of proper ones, we're leaving the time reversal and parity off to the side for the time being. So just for proper Lorentz transformations, the decomposition of a Lorentz transformation into a rotation and a boost is something that depends on the frame. So if you go to a different Lorentz frame, for example, you'll find what was a pure rotation in one frame is partly rotation and partly boost in a different frame. And so it's desirable to have a covariant approach to the Lie algebra of the Lorentz group, as well as the one that we've just developed. So I'm gonna in some ways repeat what I just did about infinitesimal Lorentz transformations, but do it from a covariant standpoint. So here's how this works. Let's go back to the definition of the Lorentz transformation in terms of matrices. Lambda transpose G lambda is equal to G. And let's say that our Lorentz transformation is infinitesimal, so I'll write lambda as identity, plus a small correction I'll write as epsilon c, where epsilon is just a small scale parameter that we make it as small as we want in order to make the correction small. Really, the epsilon serves a psychological purpose just to remind us that the correction term is small. After a while, I'll drop it. In any case, if I take this lambda and I plug it into this equation above, then what we get is identity plus epsilon times C transpose times G times identity plus epsilon times C is equal to G. And if you expand this out and keep first order terms, what you get is C transpose G plus G times C is equal to 0. This can also be written as G times C transpose plus G times C equals 0. That's because when you transpose something, you need to reverse the order and transpose the factors, but the G matrix is already symmetric, so its transpose is equal to itself. And so these two terms are actually the same. In any case, in the final form, you can see what this implies is that the matrix G times C is antisymmetric. And perhaps you recall that when we were studying the Lie algebra of the ordinary rotation group, O3, or SO3, we found that the Lie algebra consisted of antisymmetric matrices. And this is now a generalization of that fact, which is appearing here. These are now 4x4 antisymmetric matrices. So this leads us to define a basis of antisymmetric matrices, of now 4x4 antisymmetric matrices. And here's how I'll do this. Let's define a matrix I'll call A. A stands for antisymmetric, mu nu like this. And this is defined this way. It has a 1 in the slot mu nu. It has a -1 in slot nu mu in the other order. And it has 0 elsewhere. The reason I put the mu nu in parentheses here is that the mu and the nu are not the components of the matrix, they're labels of the matrix. And then I'll try to use that convention of using parentheses about when I want to label matrices to distinguish them from their components. So to give you an example then of such a matrix, the A01 looks like this. It's the matrix that has a 1, 0, 1, 0, 0 in the first row, -1, 0, 0 in the second row, and then zeros everywhere else. That's what this is. That gives you the idea of these matrices. If you let mu and nu run over all the possible values, you get 16 matrices, but they aren't all independent of each other. In fact, it's easy to see that A mu nu is equal to minus A nu mu. And in particular, if you have two of the numbers are the same, for example, A00, the matrix vanishes. So what this means is there's only 6 linearly independent A mu nus. And we can get the 6 linearly independent ones by demanding that the indices are in ascending order so that mu is less than nu. That gives us, for example, A01, A02, A03, A12, A13, and A23. And you can see here that there's 6 of them. These are all linearly independent. And an arbitrary 4x4 antisymmetric matrix can be represented as a linear combination of these 6. All right. Now a minute ago, in fact, you can still see it here, is that if C is the correction term to a Lorentz transformation, then G times C is antisymmetric. So what that means is that the G times C can be written as a sum of where the indices are in order mu less than nu of some coefficients I'll call theta mu nu times the A mu nus. Understand this equation. This is an antisymmetric 4x4 matrix. The A mu nus with the in ascending order in the indices form a basis of antisymmetric matrices, and the theta mu nus is a collection of numbers which are the expansion coefficients. Here they're defined for the case mu is less than nu. Okay. Now, however, having defined them for mu less than nu, let's define theta mu nu for the case of mu greater than or equal to nu. Let's define theta mu nu is equal to minus theta nu mu. thereby promoting these coefficients you see into an 4x4 antisymmetric matrix of numbers. If we do this, then we can write GC in the following form as 1/2 an unrestricted sum on mu and nu of theta mu nu times A mu nu. And such unrestricted sums are more convenient than ones where we're restricting the sum on the indices. In fact, if we use the Einstein summation convention, we don't even need the sum symbol here because it's understood with repeated indices. And so to write it out again, let me just do this. This now gives us this representation, theta mu nu times A mu nu, like this. Okay, and remember, by the way, that lambda was equal to identity plus epsilon times C, so that C was the correction matrix for a Lorentz transformation, thereby being a member of the Lie algebra. That's what that means. So to get C, which is going to appear in the infinitesimal Lorentz transformation, I need to clear the G. So let me multiply through by G inverse. And let me make a following definition. Let me define script J mu nu is equal to G inverse times A mu nu. Because if I do this and multiplying by G inverse here, what we get is that C is equal to 1/2 theta mu nu times script J mu nu, like so. All right. And so then this means the infinitesimal Lorentz transformation lambda is equal to identity plus the C, I'll just copy it, 1/2 theta mu nu times the J mu nu. I've dropped the epsilon now, but if you like, the epsilon could be absorbed into the expansion coefficients J theta, which you can now think of as being small, that if the theta mu nu's are much less than 1, these expansion coefficients, then this gives us an arbitrary infinitesimal Lorentz transformation. Okay. Let me say some things about these matrices, the antisymmetric basis A mu nu and the closely related J, which is just G inverse times A. Let me say something about the components of them. The components are easy to write down. If I have A mu nu and I want the alpha beta component of it like this, well, this is Kronecker delta mu alpha, Kronecker delta nu beta, minus the same thing with mu and nu swapped, nu delta nu alpha, delta mu beta, like so. And the idea is that this first pair of Kronecker deltas puts a +1 in slot mu and nu, as you can see if you look at it. And the second one puts a -1 in the opposite slot nu mu. That's just was our definition of the A's. So this is pretty clear what this does. Now then, when I multiply by G inverse here, the A index by G inverse, this is the contravariant metric tensor. It just raises the first index, which here is the alpha. So this means that the J mu nu, like this, first index is now raised alpha beta, like so. This is equal to G mu alpha. I just need to raise the alpha index, you see, delta nu beta minus G nu alpha delta mu beta. And let me box this equation because it'll pop up again, maybe not in tonight's lecture, but we'll need it a little bit down the line for some of the manipulations we want to do. But anyway, there it is, the explicit formula for these J matrices. So now at this point, we have two different versions of an infinitesimal Lorentz transformation. We've got the is equal to the identity plus theta times script J plus lambda vector times script K. That's what we did by splitting into rotations and boosts. But it's also equal to theta. It's also the identity plus 1/2 theta mu nu times script J mu nu. And so these two expressions have to be the same because they're both infinitesimal Lorentz transformations. And what that means is that the script J mu nu matrices, there's 6 linearly independent ones of them, and they must be somehow the J's and the K's, you see, related to them. And likewise, the antisymmetric matrix of expansion coefficients theta mu nu, of which there are 6 independent of those two, they must be related to or equal to somehow the 3 vectors, the theta vector and the lambda vector for the rotations and boosts. And it's completely straightforward to work that out. You just need to write out the components of these J matrices and compare to the definitions of script J and script K. And if you do, here's what you find. first of all, I'll do the rotational part first. You find that script j, let me put it I, I'll put parentheses around the indices that label the matrices. Script j sub I is equal to epsilon ijk times script j sub jk, like, or super jk, like this. Or the inverse relation is that this should be a factor of a half here. And the inverse relation is that script jk, or script ij, like this, script j superscript ij is equal to epsilon ijk j sub k, like so. Similarly, the corresponding theta vectors are that theta I is equal to 1/2 epsilon ijk theta jk, or theta jk is equal to epsilon ijk theta k. This is the connection between the parameters. As far as the boosts are concerned, ki is equal to j0i, which is equal to minus ji0. And lambda I is equal to theta 0i, which is equal to minus theta I0, like so. And this is how it works for the boosts. Okay, so this is what you find in connecting together these two different versions of the Lie algebra when we, number one, split it up into rotations and boosts, and on the other hand, where we make it completely covariant, of which this is the covariant expression for an infinitesimal Lorentz transformation. Both of these are infinitesimal formulas. All right. Are there any, this summarizes all I want to say now about infinitesimal Lorentz transformations. Are there any questions about this? Okay. Let me go back to finite Lorentz transformations. We know how to make those. Well, let's see. I think there was something I forgot to mention. Let me go back to this. Yes, there was something I forgot to mention. In the case of an infinitesimal boost, we wrote it in two ways. Let me put it this way: is that b of b hat comma lambda is equal to identity plus lambda vector dotted into k, and that's equal to identity plus lambda scalar times b hat dotted into k. And this is true when lambda is much less than 1. Okay. Now, although this is a formula for an infinitesimal boost, we can sort of bootstrap our way up to finite boosts with finite rapidities, finite velocity, that is to say finite velocities of boosts. I just made it worse. I'm trying to make it better here, make it brighter here. Oops, now I messed it up. Get it right. All right, good. All right, good. Now, yeah, so here's what I want to say. We can bootstrap ourselves up from an infinitesimal operation to a finite one. We've done this actually a number of times already in this semester. We do it like this. Let's suppose lambda is not small. And we're interested in b of b hat comma lambda. Now, the boosts about a fixed axis satisfy the multiplication law that if you multiply them, boosts about a fixed axis b hat, but with different rapidities. This is the b of the b hat with the sum of the rapidities. This is obviously just exactly like what happens when you carry out two rotations about a fixed axis. The angles just add. And in the case of boosts, it's the rapidities which add. So what this means is that the boost about a b hat comma lambda when lambda is not small can be written this way. Let's write it as, let's consider the boost about the same axis, but let's take the rapidity and divide it by a number, an integer n, like this. If we take this and raise this to the nth power, then this is an identity. This is exactly equal to that because we're just taking smaller boosts and composing them. Now the idea then is to let n become so large that lambda over n becomes small, and we can use the small rapidity approximation. If we do this, this makes this plausible that this is equal to the limit as n goes to infinity of identity plus I'll write it this way, is lambda times b hat dotted into k, script k, over n, raised to the nth power. All right. And now you see there's a well-known limit from ordinary calculus. Again, I've lectured on this a number of times in the past. It's the limit as n goes to infinity of 1 plus x over n to the nth power gives us e to the x, easily verified by elementary calculus. And it turns out that if x is replaced by a matrix, the same equation is true. And so this limit up here can be written as an exponential, and we obtain the following result that b of b hat comma k when, sorry, do it right, is that b of b hat comma lambda is equal to e to the power of lambda times b hat dotted into k, like this, which can also be written as e to the lambda vector dotted into k. And this applies for finite boosts, and it's the obvious analog of what we had for rotations, which I hardly need to. Hopefully by this time I hardly need to say much about it since we've seen it so many times. But you see, it's an obvious and simple generalization from rotations to boosts, in which the J generators are replaced by the K generators, and the rapidity takes the place of the vector, or the rapidity vector takes the place of the angle vector, or you can also factor it into magnitude and axis in both cases. Okay. Now, a few minutes ago, I explained to you how the boost was interpreted in the active sense when we were boosting the state of motion of a particle. We took a particle at rest and we boosted and got a particle in a certain state of motion. I'd like to say a few words now about boosting not particles, but rather fields. Not just boosting, but rotating, Lorentz transforming fields on space-time. We want to take a field on space-time and Lorentz transform it into a new field. First, let me remind you of some things we've done with fields on ordinary three-dimensional space and using ordinary rotations. The main example was a wave function of a particle x, a spinless particle. If we transform this under a rotation into a primed wave function like this, then the rule that we got was that the primed wave function evaluated at x is equal to the original wave function evaluated in the inverse rotated position x, like so. We did that last semester. If the particle has spin, then it's got an m index as well in the wave function. And if our rotation maps this into a prime function, then the rule is the following, is that psi prime sub m of x is equal to the sum on m prime of a D matrix for the spin involved of m prime, parameterized by the rotation, psi sub m prime evaluated at R inverse x. In other words, as far as the spatial dependence is concerned, you use the same R inverse rule that we use for the scalar wave function. But in addition, it's necessary to multiply the spinner itself by the D matrix, which represents the rotations for that spin value. It's that same D matrix of R. So the value of the wave function gets multiplied by the D matrix. This was a homework problem last semester. Okay, I hope you remember it. Let's take another example of rotating fields. Let's take a classical field like an electric field. Let's draw the XY plane. Let's suppose I've got a position vector out here I'll call X, position vector X. And let's say that the electric field at X is pointing off like this. So this is E of X. Now here's what I want. I want to take my electric field E of X and I want to rotate it and produce a new electric field, which I'll call E prime of X. And the question is, what is the formula for E prime of X in terms of E of X? What's the analog for electric fields of what we did up here with wave functions? Well, if I draw a picture, a geometrical picture of what you do under the rotation, it becomes kind of obvious. If I rotate this vector X into under R into a new vector, let me try to make it the same length here like this, like so that R does that to the vector X to produce a new point X prime. And at the same time, we rotate the value of the electric field, like so. And we'll define this to be the E prime of X prime. In other words, you rotate not only the point of application or evaluation of the field, but you also rotate the value of the field gets rotated as well. And so this leads to the rule then that E prime of X prime is equal to R applied to E of X. But X prime is the same thing as R times X. So if I then replace X by R inverse X to put an X, remove the X prime here and replace it by an X, then what we obtain is that E prime of X is equal to the R multiplied times E evaluated at R inverse X. Like so. So that's how classical electric field transforms under proper under rotations, under even improper ones, but proper ones we're talking about here. And you can see the analogy here is that again the spatial point transforms by the inverse matrix, and the value of the field rotates by whatever you need to rotate it by in order to rotate the value. Electric field is a vector value field, so it gets rotated by R. The spinner gets rotated by the D of S. A scalar field doesn't get rotated by anything because it's a scalar. This is the general rule. Anyway, once you see this pattern, you realize how fields on space-time, that's to say in four-dimensional space, should transform under Lorentz transformations. Let's let X be shorthand for CT X vector like this. And let's talk about, let's say, a scalar field. A scalar field, by the way, is an example of this is the Klein-Gordon wave function. So let's take that one of X like this. So if I have the Klein-Gordon wave function of X, and I want to transform it under a Lorentz transformation into a Klein-Gordon wave function primed of X, what's the rule? Well, the rule is this. It's easy. It's Klein-Gordon wave function prime of X is equal to psi Klein-Gordon of evaluated at lambda inverse X. This is just like the scalar field in ordinary three-dimensional space. If I have a vector field, for example, let's call it A mu of X like this, gets mapped under lambda into A mu prime of X, then the rule should be this, is that A mu prime of X should be equal to lambda mu nu times A nu evaluated at lambda inverse X. Again, we transform the space-time point by lambda inverse, and we transform the value of the field by whatever it transforms by. If it's a vector, it transforms by lambda. Okay. So all of this is plausible on the basis of following formulas and making them look like one another, following the pattern of the formulas. But you can also attribute some physics to this as well, physical interpretation. Let's take, for example, the electromagnetic field, F mu nu of X. We want to apply a rotation to that, or not, rather a Lorentz transformation, F prime mu nu of X. According to our rules, we should have F prime mu nu of X is equal to 2 copies of the lambda matrix, lambda mu alpha, lambda nu beta, multiplying into F alpha beta, evaluated at lambda inverse of X. So I bring up electromagnetic fields because that has a physical significance, and we can think about that. What does it mean to rotate and or boost an electromagnetic field? Well, electromagnetic fields are produced by currents. They come from solving Maxwell's equations. And Maxwell's equations in relativistic notation is this. It's basically the divergence of the field tensor is the current, J nu is the current. It's logical to define the Lorentz transformed F to be the field that's produced by the Lorentz transformed current. So now how do we Lorentz transform a current? Well, this is a 4 vector, so by these rules I gave above, it ought to involve a single copy of lambda like that. But let's make it more physical, because currents are produced by charges. So here, let's make a sketch of space-time. Let's make this x and then y and z coordinates here and the time coordinate like that. Let's suppose we got the whirl line of a particle here. I'll call it x mu of proper time like this. Now, if we subject this to a Lorentz transformation lambda, then we'll say this, we'll say the Lorentz transformed world line is x prime mu is just lambda mu nu times x nu tau. The proper time tau is invariant under the Lorentz transform, so it's just moving the points of the world line. So you get a new world line over here, x prime mu of tau. Well, if there's more than, let's have some collection of particles with their world lines, they're going to produce some j. Let's Lorentz transform all those world lines into new world lines, boost them or rotate them, whatever you want, to create new state of motion for those particles. That's going to create a new current. Well, then one can show that the new current transforms by precisely this transformation law. And then once that's given, that means the right-hand side of Maxwell's equations transforms by this transformation law. One can then show that the solution of Maxwell's equations transforms according to this law. So in other words, these transformation laws that I'm writing down here can all be traced back to, in the case of electromagnetism anyway, they can be traced back to what it means to take a particle in some state of motion and to rotate it or boost it to put it into a new state of motion. So all of that is a consistent scheme in terms of how fields transform. Are there any questions about that before I go on? All right, if not, then the next topic is going to be how the Dirac equation transforms under Lorentz transformations. Let's go back to the Dirac equation for a free particle. I'll write it out as IH bar d psi dt is equal to minus IH bar C times alpha dotted into the gradient acting on psi plus MC squared beta. The alpha and the beta, I'll remind you, are 4x4 Dirac matrices that have certain properties that we've talked about. Now, this is usually regarded as the Hamiltonian or non-covariant version of the Dirac equation. It is the form of this equation is tied to a specific Lorentz frame in which the t and the x variables are defined. We're interested in how this is going to transform into a different Lorentz frame. Let's approach this by bringing the derivatives, spatial derivatives, over to the left-hand side and writing the equation this way as IH bar C, and then I'll have partial of psi with respect to CT for the time part, plus alpha dotted into gradient psi for the spatial part, is equal to MC squared beta times psi on the right-hand side. That's the term that's left over. We can factor a cap, we can cancel a factor of C, so let's do that from the equation. Now, let's clear this beta from the right-hand side. I'm going to do that by multiplying through both sides of this equation by the matrix beta, because beta squared is equal to 1. So on the left-hand side, what we get is IH bar, and we get this. We get beta times partial with respect to CT, plus beta times alpha vector dotted into gradient. This is all acting on psi, is equal to MC times psi. All right, so this is just a rejuggling and reformulation of the free particle Dirac equation. On the right-hand side, we have a constant operator, MC, which is obviously a C number. It's obviously invariant under Lorentz transformations, has the same value in all frames. This suggests that the operator on the left-hand side should also be an invariant operator, should be a Lorentz invariant. We see appearing here the derivatives with respect to the coordinates. Here's the x0, and here's the other spatial coordinates x, y, and z. These are the components of the operator partial sub mu, which is partial with respect to x superscript mu, which is otherwise partial with respect to CT, and then the gradient operator. That's what this is. And this is a vector of operators, transforms as a covariant vector, which is why it's got a lower index. But it's being multiplied by coefficients here, the beta and the beta alpha. And since the suggestion is that the left-hand side is a Lorentz scalar, suggestion is the coefficients should form the components of a contravariant vector. So to bring that out notationally, let's make some definitions here. Let's define gamma 0 to be the same thing as beta. That means gamma 0 is a 4x4 Dirac matrix. And let's define gamma I to be equal to beta times alpha I. We'll put superscripts on the gamma. Because if we do, then the Dirac equation now becomes IH bar gamma mu partial with respect to x mu of psi is equal to MC psi, like so. And the point is that this now looks covariant. It looks like gamma is a contravariant vector, whereas the space-time gradient of psi is a covariant vector. They contract into a scalar to make something that's analogous or equivalent to the MC scalar on the right-hand side. All right, so this is now, just by changes in notation, this is now a version of the free particle Dirac equation, which looks covariant. We haven't proven that it's covariant. Notation by itself doesn't prove that. In order to prove that it's covariant, we need to show how gamma transforms under Lorentz transformations. That's a reasonably big project, and we certainly won't finish it tonight. But I got 5 minutes left. I'll at least get a start on it. Before we get into that, however, I think the first thing to do is just to tabulate the properties of the gamma matrices. The basic idea here is that the matrices alpha and beta, which were the original ones Dirac invented, are useful for a non-covariant Hamiltonian description of the Dirac equation, whereas the matrix gamma mu, like this, are convenient for a covariant description. Notice that the alpha vector here is a quote unquote 3 vector of 4x4 Dirac matrices. The gamma mu, on the other hand, is a 4 vector in relativistic notation, relativistic looking notation. It's a 4 vector of 4x4 Dirac matrices. So that's important to keep in mind when you see the symbol gamma mu. Otherwise, you'll be really confused if you don't keep that straight. The gamma mu is a 4 vector of 4x4 Dirac matrices, defined by these equations. I'll box them here. There's just the definitions of them. All right. So anything that you can say about the alpha and beta matrices can be translated in the language of the gamma matrices. And it's just, they're completely equivalent. But let's work out the properties in the language of the gamma matrices, because we'll need them as time goes on. So first of all, let's look at hermiticity properties. Let's take gamma 0 and compute its dagger. Well, gamma 0 is the same thing as beta, so that's beta dagger. But beta is Hermitian, so beta dagger is equal to beta, which is equal to gamma 0. And so what we conclude is that gamma 0 is Hermitian. Now let's look at gamma I. Gamma I dagger is equal to beta times alpha I dagger, which is equal to alpha I times beta. I reverse the order and I don't dagger the alpha and beta because they're Hermitian. However, alpha and beta anti-commute, so this is the same thing as minus beta alpha I, which is therefore the same thing as minus gamma I. And what we see then is that the gamma I is anti-Hermitian. So although the alpha and beta matrices are all 4 of them Hermitian, the gamma matrices, the gamma 0 is Hermitian, and whereas the spatial parts of gamma are anti-Hermitian. So that's the first thing to note. The next thing to address is the anti-commutation relations. We know the anti-commutation relations of alpha and beta. What about the gammas? Well, if I look at the anti-commutator of gamma 0 with gamma 0, that's the same thing as the anti-commutator of beta with beta, which is equal to 2. There's your fundamental anti-commutation relations. If I take a gamma 0 with a gamma I anti-commutator, that's equal to the anti-commutator of beta with beta alpha I. That's equal to beta times beta alpha I plus beta alpha I times beta. Now, beta alpha I is the same thing as minus alpha I beta, because the alpha and the beta anti-commute. And beta squared is the identity, so that beta squared goes out, and so does that beta squared that appears there goes out. So this becomes alpha I minus alpha I, which is equal to 0. And so we find the gamma 0 anti-commutes with gamma I. Now, how about gamma I, gamma j? This is the anti-commutator of beta alpha I with beta alpha j. I'll bring it down some for some space here. And so you just work it out. That's beta alpha I, beta alpha j, plus beta alpha j, beta alpha I. Now again, if I swap the alpha I and the beta there, I introduce a minus sign. That gives me minus beta squared alpha I alpha j. And likewise, let's swap those two, which gives another minus sign. Again, we get minus beta squared alpha j alpha I. Well, the beta squared is the identity. What's left over is the negative of the anti-commutator of the alpha I with alpha j, which is equal to minus 2 delta ij. So to summarize, the gamma 0 is 2, gamma 0 gamma I is 0, and gamma I gamma j is minus 2 delta ij. This can be summarized in a neat formula, which is this, is that the anti-commutator of gamma mu with gamma nu is equal to twice g mu nu, the metric tensor, the contravariant metric tensor. So this is the anti-commutation relations. It's an expression of the Dirac algebra written in terms of the gamma matrices, which is more compact and which looks covariant. You can see it looks covariant. We haven't proven it's covariant, but it turns out it will be. And it is obviously much more condensed than what we were dealing with in the 3+1 or Hamiltonian formulation, which involved our alpha and beta matrices. So those are the main properties of the gamma matrices. The initial ones we need anyway. All right. Now let's go back to the free particle Dirac equation in this covariant form. We can, this is it. I'm just copying from the previous page. This is it now. We can introduce the momentum operators, P mu. This is IH bar a partial sub mu, which is IH bar ddx mu. Same thing we talked about in the Klein-Gordon equation. So another way to write this is simply gamma mu P mu minus MC acting on psi is equal to 0. This is yet another way of writing the free particle Dirac equation. If we want to incorporate an interaction with the electromagnetic field, we can use the minimal coupling that says that P mu should be replaced by P mu minus Q over C A mu. And if we do this, we get gamma mu P mu minus Q over C gamma mu A mu minus MC acting on psi is equal to 0. Okay. So this is now the Dirac equation for a Dirac particle interacting with an electromagnetic field. This is a covariant version of the minimal coupling prescription. We used a 3+1 version of it earlier. What we see in this equation is the contractions between the 4-vector of 4x4 Dirac matrices here and the momentum operators P mu. Or over here with a 4-vector of numbers, this is A mu is the vector potential for the electromagnetic field. So these are actually fields, they're functions of space and time, but there are C numbers, which are contracted against the gamma mu. And such contractions between gamma mu and other objects like this are very common in the Dirac theory. And so there's a special notation that's developed for it. Instead of writing gamma mu A mu, which gets to be tedious, Feynman decided he'd just write this as an A with a slash through it. Gamma mu P mu is written with a P with a slash through it, like this. This is called the Feynman slash. And when you see it, you need to remember that what's being represented is actually a Dirac 4x4 matrix whose components are not constants, but rather are, well, in this case, they're functions of space and time. And in the second case, they're actually operators. In any case, using the Feynman slash notation, the Dirac equation in the presence of an electromagnetic field turns into P slash minus Q over C A slash minus MP acting on psi is equal to 0. And this is the most compact form for it's a covariant form, most compact form for the Dirac equation for a particle interacting with an electromagnetic field. This is equivalent to this much more complicated well, at least twice more complicated Hamiltonian version that we wrote down in earlier lectures. It's just change in notation is all. It hasn't been anything else except notational change. But it's remarkable for its compactness. It's also considerably simpler in form than the Pauli equation. And interestingly enough, it contains the Pauli equation as a limit. So all the physics in the Pauli equation is contained in this thing. And in fact, there's more physics in this than there is in the Pauli equation, because this also contains the fine structure corrections, the Darwin term, the relativistic kinetic energy in the spin orbit term, including the factor of 1/2 coming from the Thomas precession and the G factor of 2. That's all contained in this equation here. So this is a remarkable about the physics content of such a simple looking equation. All right, I'm sorry I ran over a little bit. Anyway, that's all for tonight, unless there's any questions about this. Questions?
So we saw before that alpha was basically like the velocity operator. Is gamma going to be like the 4 velocity operator?
No, it's not as simple as that.
Is there a 4 velocity operator?
There's a 4 momentum operator, which is the usual derivatives like this. Yeah, good question. Is there a 4 velocity operator? Offhand, I don't think so. I'm probably wrong. There probably is. The answer is I don't know. Let me think about it. Let me think about it, and I'll tell you the next lecture.
Thank you.
Any other questions? No, but the gamma is the basic, gives us the basic vectorial quantity that can be constructed out of the Dirac equation. And in fact, for example, it turns out that the current is constructed from the gamma mu. We'll see this coming up in a little while. All right, if there's no other questions, then I'm going to stop share screen and close down for the evening. Thank you for your attention, and I'll see you on Thursday night.